Let me start by telling you what the problem is. Suppose I have an electron just sitting around somewhere. You might think, well, I should be able to ask two very simple questions about it. Where is it? And how fast is it moving? These seem like perfectly reasonable questions. I mean, if you have a baseball, you can tell me where it is and how fast it's going. You can measure both things, no problem. But nature says no. Nature says you can't do that. Not because your equipment isn't good enough, not because you're not clever enough, but because nature itself won't let you. If you know precisely where the electron is, you can't know how fast it's moving. And if you know precisely how fast it's moving, you can't know where it is. The more accurately you know one thing, the less accurately you can know the other. Now you might say, wait a minute, Feynman, that's crazy. Why can't I know both? And that's a good question. That's exactly what everybody asked when Heisenberg first proposed this in the 1920s. Even Einstein didn't like it. He used to say, God doesn't play dice with the universe. But you know what? Nature doesn't care what Einstein thought. Nature does what it does. Let me try to show you why this happens. Imagine you want to look at an electron. How do you look at something? Well, you shine light on it, right? The light bounces off and comes to your eye or your detector, and that's how you see where it is. Okay, but here's the problem. Light isn't free. When a photon of light hits that electron, it gives it a kick. It's like throwing a bowling ball at a ping pong ball to see where the ping pong ball is. Sure, you'll find out where it was, but you've just sent it flying off in some direction, and now you don't know how fast it's going or where it's headed. You say, all right, so I'll use gentler light. I'll use light with a longer wavelength, redder light, lower energy. That'll give the electron a smaller kick, and you're right about that. But now you have another problem. Light with a long wavelength is fuzzy. It can't pinpoint the position very well. It's like trying to paint a detailed picture with a very thick brush. You can be gentle, but you can't be precise. So there's this trade-off. If you want to know the position precisely, you need short wavelength light, high energy, which kicks the electron hard and messes up your knowledge of its momentum. If you want to not disturb the momentum much, you need long wavelength light, low energy, but then you can't tell precisely where it is. And here's the remarkable thing. This isn't about your technique. This isn't about building better equipment or being more careful. This is fundamental. Heisenberg figured out that there's an actual number, a fundamental constant of nature that sets the limit. We call it h-bar, the reduced Planck constant. It's very small, about 10 to the minus 34 joule seconds. That's why you don't notice this in everyday life. But for electrons and atoms, it matters enormously. The relationship is beautiful in its simplicity. The uncertainty in position times the uncertainty in momentum must be greater than or equal to h-bar divided by 2. We write it like this. Delta x times delta p is greater than or equal to h-bar over 2. Delta just means uncertainty or spread. If delta x gets smaller, meaning you know the position better, delta p must get bigger, meaning you know the momentum worse. They're inversely related. Now let me tell you why this isn't just some annoying technical detail. This principle is absolutely essential for explaining why matter exists the way it does. Let me give you an example that I think is wonderful. Why doesn't an atom collapse? You've got an electron negatively charged, attracted to a nucleus, positively charged. The electrical force is pulling them together. Why doesn't the electron just fall into the nucleus? In classical physics, it should. It's like the Earth and the Sun, except with electrical forces instead of gravity. The electron should spiral in and sit right on top of the proton, but it doesn't. And the reason it doesn't is the uncertainty principle. Look, if the electron were to sit right on the nucleus, we would know exactly where it is. Its uncertainty in position would be tiny, about 10 to the minus 15 meters, the size of the nucleus. But if delta x is tiny, then delta p must be huge. The electron would have enormous uncertainty in momentum, which means it would be moving very fast on average. With all that kinetic energy, it would just fly away. The electrical attraction couldn't hold it. So what happens? The atom finds a compromise. The electron spreads out over a larger region, about 10 to the minus 10 meters. This is the size of an atom. It's like the electron is jiggling around, uncertain about where it is, uncertain about how fast it's moving, and this jiggling keeps it from collapsing. The uncertainty principle is what holds the atom together by keeping it apart. Isn't that beautiful? The very thing that makes matter stable, the reason you don't fall through the floor, the reason atoms have size, is this quantum mechanical principle that says you can't know everything precisely. Here's another thing. Even at absolute zero temperature, when you cool everything down as much as possible, atoms still move. They still jiggle. Why? Because if they stop moving completely, we would know their momentum exactly. It would be zero, and we would know where they are. That violates the uncertainty principle. So even at the coldest possible temperature, there's still what we call zero-point energy. Everything is always wiggling just a little bit. Now, I want to be very clear about something that confuses a lot of people. This isn't about measurement disturbing things in some ordinary way. It's not like measuring the temperature of your coffee by sticking a thermometer in it and cooling it down. That's just clumsiness. The uncertainty principle is much deeper than that. The problem is that the electron doesn't have a precise position and momentum at the same time. It's not that it has them and we just can't measure them both. It actually doesn't have them. The electron is fundamentally fuzzy. Position and momentum aren't things that exist simultaneously with definite values. Nature is blurry at small scales. This is what bothered Einstein so much. He wanted to believe that particles had definite properties whether we measured them or not. But experiment after experiment has shown that nature doesn't work that way. You can't design any apparatus, no matter how clever, to get around this principle. People have tried. Nobody has succeeded. If someone does, quantum mechanics as we know it would collapse. The whole theory would have to be thrown out. Let me give you a concrete experiment to show you how this works. Suppose I have a wall with two holes in it, and I'm shooting electrons at it. The electrons can go through hole 1 or hole 2. On the other side, I have a screen that detects where they hit. If I don't try to figure out which hole the electron went through, I get an interference pattern. The electrons act like waves. There are places where many electrons hit and places where almost none hit in alternating stripes. It's beautiful. It's exactly what waves do when they go through two openings. But now suppose I want to know which hole each electron went through. I put a light source near the holes to watch the electrons. When the light bounces off an electron, I can tell which hole it went through. But the moment I do that, the interference pattern disappears. The electrons start behaving like particles, making two bright spots on the screen instead of an interference pattern. Why? Because to see which hole the electron went through, the light had to interact with it, giving it a kick, changing its momentum. That changes exactly the information needed to create the interference pattern. The uncertainty principle tells us it's impossible to design an apparatus that can determine which hole the electron goes through without destroying the interference pattern. This is what Heisenberg meant when he said there's a fundamental limitation on our experimental capabilities. It's not a limitation of technology. It's a limitation of nature. Now, you might be wondering, does this apply to everything? Does it apply to you and me? And the answer is yes, technically. But remember that tiny number, h bar 10 to the minus 34. For something as massive as a person or even a grain of sand, the uncertainties are so unbelievably small that you'd never notice them. If I tell you where a baseball is to within a millimeter, the uncertainty in its velocity is so tiny, about 10 to the minus 30 meters per second, that it's completely negligible. But for an electron with its tiny mass, the effects are enormous. The uncertainty principle dominates everything about how atoms and molecules behave. It's the whole ball game. Let me tell you about another pair of quantities that have this same uncertainty relationship: energy and time. If something happens very quickly, in a very short time interval, there must be a large uncertainty in the energy. This explains all sorts of things. For instance, an excited atom doesn't stay excited forever. It emits a photon and drops to a lower energy level. But that emission doesn't take zero time. It takes a little bit of time. And during that time, the energy is uncertain. This uncertainty in energy means the photon that comes out doesn't have exactly one frequency. It has a small range of frequencies. That's why spectral lines aren't infinitely sharp. Or think about this. In quantum mechanics, pairs of particles can pop into existence out of nothing for a very short time. An electron and its antiparticle, a positron, can appear for a moment. Where does the energy come from? Well, if they exist for only a very short time, delta T is small, so delta E can be large. Energy can be borrowed from the vacuum as long as it's paid back quickly enough. These are called virtual particles, and they have real effects. They affect how electrons interact with each other. The whole structure of quantum mechanics rests on the uncertainty principle. Every prediction we make, every calculation we do, assumes it's true. And every experiment confirms it. It's been tested in countless ways, and it always holds up. I should tell you something else. When you first learn about this, you might think, well, that's just how quantum mechanics works in this particular mathematical formulation. Maybe there's another way to describe nature that doesn't have this problem. But no, the uncertainty principle isn't just a feature of the formalism. It's woven into the fabric of quantum mechanics so deeply that if you could somehow violate it, all your predictions would become inconsistent. You'd start predicting things that contradict each other. So what do we make of all this? We have to change the way we think about nature. We can't think of electrons as little balls with definite positions and momenta. We have to think of them as, well, as something else. Something that's spread out, that's described by probabilities, that doesn't have definite values for certain properties until we measure them. And this brings up all sorts of philosophical questions. What does it mean for something to not have a definite position? What happens when we measure it and it suddenly does have a position? These are deep questions, and physicists still argue about what they mean. But here's what I think is the right way to look at it. Nature tells us how she is through experiment. We do experiments, we get results, and we find that we need this uncertainty principle to make sense of those results. It doesn't matter if it seems strange or if it conflicts with our everyday intuition. Our intuition was built for dealing with rocks and trees and animals, not electrons. The remarkable thing is that once you accept this strangeness, once you work with quantum mechanics and use the uncertainty principle, you can calculate things with incredible precision. You can predict how atoms behave, how molecules form, how materials conduct electricity, how lasers work, how the sun shines. All of modern technology, from computers to nuclear power to medical imaging, relies on our understanding of quantum mechanics and the uncertainty principle. So yes, it's strange. Yes, it's counterintuitive, but it's how nature works. And that's far more interesting than if nature worked the way we initially expected. The universe is under no obligation to make sense to you. Our job is to figure out the rules it actually follows, not the rules we think it should follow. And you know what? Once you get used to it, there's something beautiful about the uncertainty principle. It says that nature has a fundamental graininess, a fundamental limit to how finely things can be specified. There's a kind of democracy to it. Position and momentum, energy and time, they're on equal footing. You can't maximize your knowledge of one without sacrificing knowledge of the other. It also means that nature is never completely still, never completely determined. There's always some wiggle room, some uncertainty, some fundamental randomness. I think that's wonderful. It means the universe isn't a clockwork mechanism, rigidly following predetermined paths. There's some looseness, some freedom built into the structure of reality. Now, does this mean anything can happen? Of course not. Quantum mechanics is extremely precise about calculating probabilities. We can predict exactly how likely different outcomes are. We just can't predict which specific outcome will occur in a single instance. But when you have many particles, statistical predictions become very accurate. The uncertainty principle is one of those ideas that changes how you see the world. Once you understand it, or at least once you understand as much as anyone can, you realize that reality is fundamentally different from what we imagined. Particles aren't little billiard balls. Waves aren't just ripples in some medium. Nature is something stranger and more subtle. And that's what I love about physics. Every time we look more carefully at nature, every time we do more precise experiments, we find something surprising. The universe is far more interesting than we ever suspected. The uncertainty principle is just one example of how nature works in ways we never would have guessed. So we can't know everything. We can't measure both position and momentum precisely. We can't pin down energy and time simultaneously. And that's not a failure of physics. That's physics telling us something profound about the universe we live in. And you know, I think Heisenberg deserves a lot of credit for figuring this out. He saw that there was a fundamental limitation built into the structure of quantum mechanics, and he had the courage to say so. A lot of people didn't want to believe it, but he was right. the uncertainty principle is one of the pillars of modern physics. Without it, we couldn't explain atoms, we couldn't explain chemistry, we couldn't explain why matter is stable. It's absolutely essential, and it's strange and wonderful and true. That's nature for you. Always more interesting than our imagination.